Join these symposiums and also enjoys the city, especially the Punta Arenas restaurants. Well, now we have two more plenary talks. The first one is by Dr. Joa Liang. Is here, I think. Okay. He's from the China University of Geoscience, Beijing. Please welcome. The floor is yours.
Hola, buenos días. Firstly, I'd like to thank the committee giving me this opportunity to share our new results. And the title is Tectonic Process of the Drip Passage, Control the Cenozoic Million Scale Ocean and Climate Cycles. And actually, I have presented some of these results on the SCA meeting. And this is a reversed version of our paper. And with the help of these co-authors, paper has been submitted to Nature Geoscience, and now it's under review. So any comments and suggestions, welcome. So we know that we are facing a very serious problem about the higher concentration of atmosphere CO2. We can see that the concentration of the CO2 has exceeds the glacial and interglacial cycles. So it has become a geological problem. So we know that we as humans, we have great powers. Yeah, we release a lot of CO2, and now it's almost close to the Pliocene level 3 million years ago. So why we study the geological time scales? Because understanding the million scale oceanic controls is very urgent, and because they may trigger irreversible thresholds, such as the polar ice sheet collapse and also the carbon cycle disturbs. We know that the past is the history is the mirror of the future. And to predict the climate change of the future, we can use the Cenozoic records to do this, because the Cenozoic Earth has changed from a warm period to a cool period with the formation of the polar ice sheet. So if we do not care about the CO2, we might go back to the Eocene warming world. And with the melting of the ice sheet, the sea level rise, and all of us will be influenced by this process. And we also know that we are living in a world with different cycles. We know there are orbital cycles, glacial, interglacial, and there are also cycles from during in the human time scales, decades, years. And we also have the tectonic scales. It's a million-year scale. And we know that the CO2 has already, at about Pliocene level, it's a tectonic problem. So this is a very good result, and mainly from the ocean drilling program. I think this is one of the most contribution of this program. We know that the world has become from a warm world to the cold world, and also there's a change of the carbon circulation. And actually, we can see there are different cycles in this data. It's a decrease, an increase, decrease, increase, decrease, increase, decrease, increase. So actually, we don't know what controls this process. Yeah. So I think that one of the most contribution to the 20th geology is the finding of the Milankovitch cycles, orbital cycles. So we don't know tectonic cycles. What the driver of these cycles? So different scientists have proposed different theories to explain these tectonic cycles, including the opening of the Drake Passage and also the uplift of the Tibetan Plateau. Because the uplift of this plateau can expose a lot of fresh rocks, and it can enhance the chemical weathering, and then the enhanced chemical weathering can absorb a lot of CO2 and make the world cooler and cooler. And also there are different theories, including the weathering of the lower latitude mafic rocks. However, the uplift of the Tibetan Plateau cannot explain the tectonic cycles. Because we can see this is the reconstruction of the uplift history, of the paleo elevation of the Tibetan Plateau at different time scales. We cannot see cycles. Yeah. Meanwhile, the present reconstruction of the Drake Passage mainly show that there is a gradual opening of this passage. Yeah, no cycles. So to solve this problem, we propose that we still should also concentrate on the Antarctic, Southern Ocean, because Southern Ocean is the center of our ocean. We can see there is a stronger Antarctic circumpolar current. It connects the Pacific Ocean, Atlantic Ocean, and Indian Ocean. And also this is the densest Antarctic bottom water. It sinks and then upwelling at lower latitude. Yeah, it controls all these circulations. So Drake Passage here is very important. Why? Because the opening of this passage can induce the formation of the ACC. And the close of this passage can also stop the ACC. And it can change the circulation pattern of this current. And then the changed ACC can change the AABW. And the changed AABW will influence the upwelling process. So it will change all this world's ocean circulation. We know that the evidence for supporting the Milankovitch cycles, this paper, and from these two drilling sites, it's also the evidence from the Southern Ocean. So what about the tectonic cycles? This is a reconstruction of the before the opening of the passage. We can see there are different micro-continents around these areas, and then during the opening of this passage, this micro-continent separated from the northern part of the Antarctic Peninsula and also the Patagonia Andes. This is very complicated areas. This is the Antarctic plate and the Phoenix plate, Antarctic Peninsula, and this is the Atlantic Ocean and the South America plate. This is also the South America plate. So this is the Scots plate. We have the West Scots Basin, Central, and the East. There's an old subduction dune, ancestral South Sandwich subduction dune, and this is now the new South Sandwich subduction dune. We can see from the seismic image that this is the Phoenix plate. It's a big plate here, and it's almost seized, but it still works. It still continues. It's very slow speed. And this is the South America plate. It has been abandoned. It's a small scale. This is the South Sandwich plate. This is the basic geological background of these areas. But you also should remember that there are lots small blocks in this area. So we can see from the geological profiles, these are different blocks, or these blocks. This is very flat. You should remember, flat. This block is separated from the North Antarctic Peninsula. This is a plate reconstruction from different studies, and basically they are almost the same. We can see this 5678 is 5678. We can restore, reconstruct this place to their original place before the separation. And also this is the recent publication based on the plate reconstruct data, and also show this small place at these areas. So we think that the subduction of the Phoenix plate, and also you can see the Paleo-Pacific plate, will change the crustal thickness of these areas, including these small blocks. And the change of the crustal thickness can change the paleo elevation of these blocks. So we use different methods to prove our assumption. We use the plate reconstruction, basically use the paleomagnetic data, and also the seafloor magnetic data. And we reconstruct the crustal thickness along this belt from Southern Patagonia Andes, and these small blocks, and the Antarctic Peninsula, as many on the South Shetland Islands, because it's very close to the Scotch Sea. And then we use the crustal thickness data to reconstruct the paleo elevation variation along this belt, with the area as a static model. At last, we use the Earth system modeling to find the truly dynamics behind all these changes. This paper has been published on GIL, and we did the paleomagnetic study, and we found that there is a clockwise rotation of the Antarctic Peninsula during about 62 million years, between the 62 to the 59. So the clockwise rotation of this in this period may have induced the initial formation of the Drake Passage, because we also find the corresponding change of the proxies in the Pacific Ocean and also Atlantic Ocean. And this period also corresponding to a smaller scale global cooling during the Pleistocene. And we can see that before the opening of this passage, but it's very shallow maybe. Before the opening of the passage, there is a cycle here. And I think this may explain the finding of the spreading of the seas from Patagonia Andes to the Australia, just as shown Marcelo Lippi yesterday. So the seeds and animals can migrate from the South America, Antarctic Peninsula, to the Australia. So after the opening of this passage, there's the global circulation pattern changed. Firstly, the Atlantic Ocean circulation has been weakened. So the salinity decreased, because we know that the high salinity water mainly in the lower latitude. So the stronger ACC has decreased the current intensity here. So there's a decrease of the salinity, and we can see that this is Atlantic data. This is Atlantic data. The Hydra's frequency also decreased, because the bottom water weak. Yeah. But the ACC brings a lot of high salinity water to the Pacific Ocean. So the AABW in this area becomes stronger. So we can see the increase of the Hydra's frequency, and also the dissolved oxygen index. Yeah. A lot high salinity water here. Yeah, all this changed. We can see that this is from the simulation, the model simulation. This is sorry. Yeah, The model simulation has shown that there's a decrease of the temperature. No, this one, sorry. But we can see the change of the ABW. The whole ABW becomes stronger because the Pacific Ocean is much bigger. Yeah. So the global ABW increased. This is temperature. We can see that after the opening of this passage, the Southern Ocean become cooler. And we know that the ABW can bring all this cold water into the deep ocean. Yeah. So this period, we can see the initial opening of the drake. So what about the falling period? This is very important. Yeah. So back to this figure, we can see that all these small continents here. Yeah. So we propose that the subduction of the Pacific Ocean will change the crustal thickness of this area, and also the paleo elevation of all these microcontinents. So we use all these different proxies to reconstruct the thickness. This is the theory. We can see there is a very good correlation between all these proxies and the morphal depths. Morphal depths also the crustal thickness. So all this data from the South America, Scotch Sea, and the northern part of the Antarctic Peninsula, different proxies show the almost consistent results. Yeah, there's a change of this crustal thickness. Then we use the areostatic static model, and basically it's the thick crust can induce the higher elevation. So the thin in the lower elevation. So we summarized about 358 data across these areas, and we found that there is a very good correlation between the crust thickness and elevation. So use this relationship, we can reconstruct the paleo elevation. Okay, different data, different areas, we show the almost consistent pattern. Also, the geological evidence. So our data should be supported by the geological data. This is the fossil from the South Shetland Islands, the King George Island, Cape Merrill, the leaf, and you can see that it's about 21 or 22 million years. Yeah, maybe it's very close to the sea level. Sometimes maybe it's uplifted above the sea level. So we can see the leaf and also the fossils, the very shallow. Yeah. There are also some other records from the Polo Formation, also in the King George Island. It's also close to sea level. And we also have the Port Thomas Formation. It's maybe the first Alpine glaciers in West Antarctic. It's 45 to 41 million years above sea level. This is the picture. Okay, 45. This is the 45, yeah. 45 is a very important period because all these continents might uplift to the sea level. We can see the glacier. Yeah. There are also some other evidence. Firstly, Yin has proposed that the macrocontinents in the Scotch Sea might stop the deep flow. And also there are some all these microcontinents. We can see this. There are some very marine erosion at some period when this continent is above the sea level. Yeah. So what controls the paleo elevation of these microcontinents? So we did a plate reconstruction by using our paleomagnetic data and also the previous data and rotation files. So this is the ocean ridge. This is the transform fault, and we found that at the beginning of the change of all these things, the ocean ridge collide with the Antarctic Peninsula. Yeah. We calculate the convergence rate between the Pacific and the Antarctic Peninsula. We find that during the reduction of the subduction rate, there's a subsidence at these areas. Yeah. But the higher reduction rate caused the uplift of this area. All these reconstructions, we can see that the subduction of the ocean ridge here. Yeah. So it corresponds very well with the crustal thickness data. Then the geochemical data also support that these arcs, these volcanic rocks, formed by the partial melting of the depleted lithosphere metal source. So we want to build a picture of all these tectonic processes. So we also summarized the thermogeological data and also the number of the magnetic data or the volcanic rocks, and also the migration of the magmatism, and also at last the ACC strings. We can see that these gray bands correspond to the decrease of the thermogeological data. At this period corresponding the increased data, which means that the uplift and it's up and down, up and down. So the magnetism also have a peak during this period. Peak. Yeah. So the magma migrate from the eastern part to the trench world migration. Yeah, also occurred during this period. Yeah. So this is the model. Yeah, we can see this during the subduction of the ridge. There is a decrease of the subduction rate, and slab rollback occurred. There's upweighting of this atmosphere things, and there's arc magnetism. All corresponds to this data. And during the subduction of the transform fault, the subduction angle become lower. There's a compression during this period. So the crustal thickness will become thick. Yeah. So then the ACC will become stronger during the subsidence period. Crustal extension occurred during this period. So the crustal thick will reduce the strength of the ACC. So this result supported by the ACC strength. We can see the decrease, increase, decrease, increase, decrease, increase, decrease, increase, decrease, increase. So, yeah, all this data matched. Yeah. This is a simulation from the model. You can see this. This is the ridge. And when the ridge approaches the trench, there's a decrease of the rate, subduction rate, and also the rollback of the plate. Yeah. So we can see the migrate of the magma from the east to the west. It's another model. Yeah. So this is the ACC strength record. Yeah. So by using the plate reconstruction and also crustal thickness reconstruction, paleo elevation reconstruction, and the subduction process, and ACC strength record, we can finally see that the drag changed the ACC. Yeah, it controls the ACC during the Cenozoic. So then we made a model simulation. Yeah. This is the drag passage closed and open at 100 meters depth, 300, 1,000, 25,000. Yeah, first we can see that during the initial opening of the passage, the AABW becomes stronger. Yeah, this is the depth 100 minus deposit closed. Yes, it's become stronger. Yeah. So then it becomes deeper, and the ABW sinks deeper. Yeah. But it also becomes weak. Yeah. So if the geological data support our simulation, the answer is yes. We also found out that the ACC becomes stronger after the passage becomes deeper. So this is a new publication of the records of the deep sea hikers. It's all these sites across the ocean. So it can represent the global ocean situation. It's not a regional record. So we can see that during this gray band period, there's a decrease. And during this period, increase. Yeah. But the geological records match our model simulation. You can see this is about 3,500 meters. Yeah, so also, yeah, but depth is here. This it becomes small, weak, but the ABW sinks deeper. There's a strong hydrous frequency beneath this depth. We can see that this is the record below this depth. It's an increase. Yeah. So also the oxygen level in the deep ocean has decreased during this period because the host gear or the ABW becomes weak. Yeah. We can also see that the delta carbon 13 it's a decrease because the Antarctic water has a lower value of this proxy. So the weak of the ABW will induce the decrease of this proxy. Yeah. This is the sea surface salinity, and all this data show that the Southern Ocean salinity has decreased. Yeah. Why? Because the ACC becomes stronger. Yeah. ACC becomes stronger. It will limit the entrance of the high salinity water into the Southern Ocean. So the ABW becomes weak. And also the mixed layer depths increased in the Pacific Ocean. Yeah, so the ABW sinks deeper. This is the high salinity water, and it's from the Brazil and also the Indian Ocean, Australia into the Southern Ocean. The stronger ACC stopped the entrance or decreased the entrance of this water into the Southern Ocean. So salinity decreased, the ABW becomes weaker. Okay. So we also care about the temperature change during this period. We can see that our simulation shows that the north hemisphere becomes warmer and the Southern Ocean becomes cooler. And also there's the northern hemisphere becomes rainy, yeah, rainy, and the southern hemisphere becomes drier. The geological records also support our simulation. That this is from the delta oxygen and this from other proxies. We can see that the warmer, cooler, and cooler. These red lines from North Atlantic, and this blue line from the high latitude south. Yeah, cooler, warmer. So why? Why? Because the energy balance. So the north becomes warmer, south becomes cooler. Yeah, the energy should be balanced. Yeah. These records also show the same pattern. Yeah. The most important is the lithium isotope. We can see because the lithium isotope can represent the strength of the chemical weathering, silicate weathering, because it consumes the CO2. Yeah. So we can see this, the increase of the lithium isotope. Yeah, increase. So this stronger chemical weathering will consume a lot of CO2. it will reduce the temperature. Yeah, this explains why the Earth becomes cooler during the Cenozoic. This is a study about what controls the strength of the weathering. So it's mainly the temperature. You can see this is here. It's a very good correlation between the temperature and the chemical weathering, CRA or CR. So we know that this is a reconstruction of the output of the CO2 from the subduction zone and also the ocean ridge. It's so most consistent during the Cenozoic. So it's not too much CO2 has been put into the atmosphere, but the chemical weathering can consume the CO2. Yeah. So we can put all this data together. Yeah. The Drake passage subsidence due to the subduction of the Phoenix plate. Okay. Subsidence uplift, and also all these geological records and the strength of the ACC. Sorry. And also the deep sea hiatus, and also the deep sea oxygen level, delta C13, and also the global temperature lithium record. So the ACC might be the worst dam. Yeah, the worst dam. It changed all these circulations and also the patterns of the global change. So now we can, maybe we can answer some question. What controls all these geological cycles? It's the Drake passage, the Pacific Ocean, subduction, all this process. So it's like a story from the tectonics to the surface process. Finally, I would like to thank my friends from Chile, Argentina, Brazil, and also British, and also the ambassador give us valuable support. Yeah, the repassage was the key. Thank you.
Oh, thank you very much. Very beautiful presentation and very informative presentation. So we have time for some question, please. All right.
Thank you for the talk. Just a quick question for the proxy that you've got for the continental crust or crust thickness. I'm not 100% sure I understood that correctly. You're using sort of rare earth ratio, and the rocks, chemistry of these rocks, they are more basalt, right, than anything?
Pardon? I'm not very clear. Yeah.
So you used some chemical proxy for the depth, for the thickness of the crust, right?
Yeah.
And the chemistry of these rocks are more basaltic than anything, apparently, from one of the slides that you showed. And I'm just wondering, what your proxy is showing is just the depth of melting of these rocks, not really the crystal thickness. Can you comment on that?
Back to this slide. These proxies mainly can be used in the arc, only these areas. So this place is the arc. Yeah, the subduction of the Pacific Ocean created a lot of basalt and granite. So this not clear. Okay. Yeah. As this proxies has been used in different areas, from Plato or Andes, Tibetan, or Southeast Asia. Yeah, it's a very reliable proxy. Yeah.
The statement, the Drake passage is the key. What would you say people living in the future, let's say 100 years from now, people living in the future,
Yeah.
what will they say regarding things happening now what would they say? That was the key.
Yeah.
What would you say to that? Thank you.
Okay, thank you for a question. And so our purpose is to predict the future and also understanding the situation now. I'm not present too much data for the future because this is another paper. I do not have too much time to discuss this. But I can show you. Okay, this one. So we also find actually there is a change at about 10 million years. Because we can see the northern hemisphere becomes warmer. Yeah, the same situation now. Yeah, the whole Arctic Ocean have become warmer and warmer. So we think that this process has released a lot of CO2. Yeah, because the stronger weathering did not also it can also release the CO2. As it's not only consume the CO2, it also release. Not put a slide for this, but you can see that in my next paper maybe. We found that the northern hemisphere with the stronger weathering will release a lot of CO2 now. Yeah. So the ACC, we should concentrate on the strength of the ACC. Yeah. This ACC is also changing. It can change the northern hemisphere. It is the interaction between two different hemispheres. Yeah. Thank you. Yeah. I can show you further. Yeah.
Yeah, Liang, thank you very much for your talk. Since you've got that slide on, can you tell us a bit about what type of numerical simulation you use? Is that actually a full global, a global climate model that's fully coupled with ocean atmosphere and solid Earth as well? Or what exactly did you use? Because, I think we all know that, obviously the Drake passage is one of the keys. It's not the only one. There's many other gateways that act in different ways and they're all interacting with each other. And another issue, which is very difficult to reconstruct, is the atmospheric circulation in paleo times. That's almost impossible to reconstruct entirely, but modelers have tried to do this. Can you tell us a bit more about your numerical simulation?
Yeah, thank you, Carson. Very good question. And so our conclusion is only the Drake passage is the key to the cycles. Yeah, the cycles, not the whole process. We also know that there are other gateways, for example, Tasmania gateway and the Panama gateway, or this lower latitude gateway. But we found that the Drake passage uplift subsidence control these cycles. But there are also some smaller scale changes during the cycles. So other gateways may change these cycles. But Drake passage control these cycles. So this study may have established a framework to discuss the interaction between Drake and other gateways. So this is one for your answer. Yeah. The situation is the simulation is based on the community Earth system model. It's only the surface, and the boundary condition is 30 million years with the ice sheet. Because why we use this time? Because there are simulations on the 40 million years, and also the modern. So there's a gap between this simulation. So we put the 30, and also with the ice sheet. Actually, I did not present the simulation of 40 million years and also modern, because the simulation show that So before the formation of the ice sheet at EOT transition, before this is a smaller scale change. So after this, there's a stronger change, maybe caused by the ice sheet. Because when we put the ice sheet, it's both the ocean circulation, the ABW change stronger. Yeah. Also temperature. So that's why we put on this situation. Yeah, thank you.
I have a question for you about the ancestral South Sandwich Arc. That was active from 30 million years till about 12 million years. Ocean drilling data have shown, since we published the evidence for this remnant arc in the Central Scotia Sea, that for the homogenization of the Pacific and Atlantic isotopic composition just after that time, and an increase in the velocity of the Antarctic circumpolar current. How does that particular event, which had been documented to have its effect in the Antarctic circumpolar current to the east of Drake Passage and the east of the Central Scotia Sea, how does that fit into the oscillations that you postulate for Drake Passage itself?
Okay. Thank you, Ian, your question. And back to the ancestral South Sandwich subduction. Sure. Sorry. So subduction zone is here, and actually we do not have too much data about the time of the initiation of the subduction zone. Yesterday I presented age data from the intraoceanic basaltic age. It's about 97 million years, published by the British Antarctic Survey, Terry, and it's also one of our co-author. So the formation of this subduction zone may have occurred during about 100 million years, between 100 million years and 90 million years. So it's a smaller scale. We also consider the subduction of this place, but we find that the convergence rates between the Pacific and the Antarctic Peninsula has controlled the period depth change. So maybe the subduction of South American plate may have influenced, but it's not the number one controller. The number one controller should still be the Pacific Ocean. Yeah, it has a much stronger and larger place as areas. But the opening of so the subduction of these areas, we don't know. We don't know the role this, but we need more data in the future. Yeah. Thank you.
Okay, we thank once again for this very nice presentation. Thank you. Well, and now we have our second plenary talk. And for that, I invite Sebastian Marinsek. He is head of the Department of Geology of the Instituto Antártico Argentino. So please, Sebastian, the floor is yours.
Okay, good morning. Let me check. First of all, thanks to everybody, the organization. Gracias, Jorge, por la invitación. And I will try to put something together because we are in a Earth Science Symposium. We have several sessions, different topics, and there are connections between them. Antarctica is huge, so I try to put several things together and some experiences to talk about the whole continent and the whole Earth system. Here. Okay, Antarctic continent, here's a picture. We know it's very huge, 14,000 million square kilometers in surface. The volume of ice over the rock, because we have the rock, and over the rock, on the rock, we have more than 25 million square kilometers of ice. And it's a huge amount of ice. And if we put in the graph the water on Earth, this is the distribution of the water on Earth. Of course, most of them is in the oceans. And then from the fresh water, this is what the water we need to live. Only 3% is fresh water, and most of them are in the glaciers. Then we have, of course, groundwater and what is near us visible. From all these glaciers here, almost 70%, 90% of the glaciers are in Antarctica. That means that the 60% of all the glaciers in the world are in Antarctica. So the huge water reservoir, of fresh water reservoir, is there. It doesn't mean we can take from Antarctica and take the water to the places in the world that they are dry or they have no access to water, but it's there, and something we have to care. And something also that is very important, and this water is equivalent, if we can melt all the ice, is equivalent to a very high sea level rise. So here we have a first connection with the whole planet. If something happened with the ice in Antarctica, the level rise, a lot of things will change, but for sure, one thing that it will change is the life of people, of the million of people that are living by the coast. So it is not like only science connection, it is human activity, economy, several connections. If something happened with the ice in Antarctica, that's one of the reasons we study this in the whole planet. Then, besides the ice that is grounded, we have the principal ice shelf here, two big ones, 1 million square kilometers, and they are like the caps of the tanks of the Antarctica. We know that if something happened with the big ice shelf, then the dynamics of the glacier will change, and also will change the same what happened with the sea level rise. So this is important also, and we have seen this last 2 weeks, last 2 days. Works done below the ice shelf, interactions, past interaction. What was in the? This is maybe a picture from the present, but several investigations and research of what has happened below the ice shelf are trying to explain what can be in the future. So yesterday we saw the research on the both West and East Antarctic ice shelf. Here we have changes in this ice shelf. We can see that several of them have a lot of, the red one, have changed loss in ice, and they are the hotspots where different programs try to reach the place, do research, do field campaigns. It's not so easy. We know here, we were talking about the icebreakers, aircraft, and it's something about a lot of money, and this is important because they're changing. Other thing we have is the sea ice. You can see this is from 2 days ago, and this is the coverage of the sea ice around Antarctica. We are talking about 14 million of the ice cover of the Antarctica, but we can see that the sea ice today is more than the Antarctica. So the total area of the icy area is double at the moment, and of course it changes the albedo, it changes the energy absorption, dynamics. Sea ice also interact with the front of the glaciers. If we have some places like here today, for example, there is no sea ice in this area, so glaciers that are there are interacting with the ocean differently than the glaciers that are here, for example, just in the other part of the peninsula. The same latitude, not the same weather, but at the same latitude you have glaciers with and without sea ice, so the dynamics are completely different. And this is the graph for the last 4 years. All of us know about the change in the pattern since 2022. There was some news in the last years about supposedly a big iceberg coming from Antarctica, but it was just a sea ice difference in the concentration. And we can see the brown one is 2022, was below the media. Then we had a minimum record on 2023, and following years, and these are a bit better, but not so much. We are not, at the moment, going back to the sea ice extension that we had in the past. So, unfortunately, it's just two pictures, two dates, data from the 3 or 4, from different years. Maybe you have to wait some years more to check what is the pattern of the sea ice extension, but it's something you have to take care because they interact just directly with the glacier. Other thing, this is a sea ice. Now, other connection is with the oceans. We have the Antarctic circumpolar current, ice in contact with water, water in contact with ice. We have seen also here some images, some pictures, and research about the water going to the channels into the below the ice shelf in West Antarctic ice shelf, the Ross ice shelf. There are different ice shelf and different interaction from the water, cold water, deep cold water, circulation. We have seen just a few minutes ago the circumpolar connections with the whole continent, not only Antarctica, only the glaciers, but ice shelves are the first that are in contact with these dynamic modifications. And again, ice shelves are the cap of the tank of Antarctica, so it's important. For example, this is in Crane Glacier as I told before, in the east coast of Antarctic Peninsula, northern part, and the glacier, you can see that ends here, but we have here in the front of the glacier an ice melange that it was changing last 20 years from a lot of ice, maybe nothing icy melange, and after this year we had a very huge and concentrated ice melange during more than 10 years. So the glacier started to move again forward, not like an ice shelf, because the Larsen ice shelf has disintegrated here 1 year before the first picture here. But after 10 years of ice melange on the front of the glacier dynamics changes again. And then last 2 years with the sea ice concentration, this minimum sea ice concentration around the whole Antarctica and changes from 2002, 22, 23, 24, changes also the pattern in the sea ice concentration on the east part of Peninsula Antarctica, Antarctic Peninsula. You can see we have been during 10 years a very high concentration, so it was stuck, the glacier was stuck and moving different, and after the sea ice was lowering all around the continent, it also affected the glacier, changing the dynamics and changing the front position. You can see how it retreated very, very fast, and that's the reason we try to put 2 GPS systems on the glacier to track it, and there is something that is still in process for be published, but we can see that this connection between water, sea ice, glacier, land, the air part of the ice is the one part of the Earth system of Antarctica, are interacting in everywhere. This is a small spot because you can see here. Let me go back. This is the glacier. This is one of the longest in the Antarctic Peninsula. This is the region, and you can see the huge Antarctica. So this is the only spot, but it's a sample of what can happen with different other glaciers all around Antarctica. Also, we have something below the surface. All the movement. Also, today we have a talk about this. What happens below the surface? And this is also something affecting not only Antarctica, but all the planet. This is a seismographic network around Antarctica. There are several instruments from different countries. There are not so much you can see, but they are powerful because the earthquakes move around all Antarctica, all the planet, and reach everywhere, sometimes with higher magnitude than others. But with this, in an international collaboration, we can have a picture about what is happening with the seismic condition everywhere, every time. For example, this is the last big event, 8.8 in Kamchatka, and this is the record for Orcada Station, one of the oldest stations all around Antarctica. And you can see, if you look for in Google and try to locate Kamchatka or Orcada Station, they're just opposite in the planet. So it's like here and the other part of the world, the planet is this the case? It's about on the surface. If you go by ship, by plane, more than 18,000 kilometers, but the wave was reached and recorded in that day in Antarctica, just in the opposite side of the world. And here we have another connection with the human activities. The first day, I guess on Monday, we talk about the tsunamis alert here in the Pacific coast. One of the guys of Chilean, I guess it was the Navy, was talking about the tsunamis alert. And this is something that's happened. We have different, others earthquakes in the past, huge one here in Chile in 2010. This was recorded in Belgrano Station, that is 77 degrees latitude south, and also distance, very long distances, and this is what interacts the rest of the planet with Antarctica, and Antarctica also with the rest of the planet, because we have the Drake Passage, explained you before, and we have at the moment alert of seismic activity in the Drake Passage. Yesterday and on Monday, there was some small earthquake seismic activity, not so enough to move the buildings or to be sense for people, but the seismographers are sending alarms every day about activity in the Drake Passage, in the north part of the Antarctic Peninsula. So this is something important for the tsunami detection that must be enhanced, but the data is over there almost in real time, and something that we need to this connection with the rest of the world and human activity we are in different countries to improve. Another example is, this is in 20 years ago, but it was a very huge magnitude earthquake during winter near Orcada Station again. I can show you the station. This is the station, just at the sea level. And the station is north, and it is to the north, this is to the south, and it has water to the north and to the south. So this kind of earthquake, you can imagine what happened with the tsunami. Okay, you cannot imagine because it was winter. It was sea ice, frozen the sea, the whole sea from both sides of the station, and you can see here the waves, the cracks of the waves. The earthquake make waves crack it all the sea ice pack, and then nothing happened to the station. But we were lucky because it was in August. But this happens a day like this, the history is completely different. So, and there was a connection just when the earthquake near the station. This is near the passage. You have seen the tectonic in the area. It's not so easy. So this is something that we are improving on the communication. We are improving this kind of tsunami alerts. At the moment, it's just we call the guy, or the guy called us, there is an earthquake somewhere, and they say, okay, no problem, there is no problem with the station, take care, don't take care, but something that we had to improve, and also was taking part in the talks in COMNAP, in ATCM meetings. This is something, because at the moment we are just doing science, but this kind of science can help and human activities. Here is a research station, there are lives there, but in other cases, you have several economic problems if something happened to a city. We have seen tsunamis in other parts of the world, so this is something that can happen in Antarctica also, and is something related to earth sciences also. Let me check. What happens above the surface, over the surface, in the air? We have warm events, fun events, atmospheric rivers. We have seen yesterday something about atmospheric rivers. This is the northern part of the Antarctic Peninsula. We have here Marambio Station. In this Vega Island, we have a mass balance program. So we set the camp there and do our work there. And last year, because of we changed the mode of going to the place and go back go back home, because we used to stay there on February only, but we need to do something else, so we stay there a few days more. And during these few days more, we were in the camp. There was an event of 60 hours continually, high-speed winds. This is not maybe this is the mean, not continuous 60 hours of 100 kilometers per hour, but maybe sometime 120, the rest of the day 80, but it was 60 hours continuous wind, but when particularly conditions, it was 10 degrees warmer and 15% drier than the previous condition. So with this, look here, the stake before the event, and look here, the stake before the event. After the event, and the sea surface, you can see snow. Here we have lost 50 centimeters of ice, mainly, and some snow also, because you can see how it was the surface here. If you look inside this hole by the stake with the GPS, you can see some snow, and at the bottom this ice. But after the event, we lost the snow and 50 centimeters, 45 centimeters of ice. Not only snow, because you can see, okay, the wind just blow the snow, nothing happens. But this is ice. It was ice, and then there was nothing. Just 60 hours of wind. And maybe when we are going every year to this place, this stake, for example, maybe the annual mass balance in this place is about 1 meter only. Losing 1 meter. This is a place that loses 1 meter every year. So if in 1 week, or maybe 2 days and a half, we lost the half of the day of the mass balance we reach every year, this is something that we cannot see every year. We have the records of the station. We go every year and record the station. We download via satellite or Wi-Fi the information, but you cannot be there and reach the place just before the event because you don't know that there will be an event. And also we cannot be there after the event because we are here, for example. So this was a maybe lucky opportunity to see what happened during this event. And this was the surface of the glacier. Look at this. Very nice, white. And look there after the event. We lost the snow and the ice. So it was at the beginning of the winter session. So we crossed the fingers to the snow came back this year. But it's something that happens several times. So and this is a connection between the Earth and the wind. And we was also looking at presentation from Dennis yesterday about atmospheric rivers that are occurring more often. And he was studying in South America. We, people from Chile, our neighbors, and we are in South America. We are both countries just in the tip of South America, the southern tip of South America. We are near to the Antarctic Peninsula, and these atmospheric rivers thus are going through South America and reaches Antarctica. Then he showed a problem he had in the camp because of one of these events, and maybe this is also an event we are just studying. This is an event that can be combined with the fun event that we experienced last year. We don't know still. Both of them are combined or only fun event or both of them. But we are looking for that because it's something related to the pattern circulation of the air, warm air, and ice doesn't like warm air. So it's important also this. And they have experienced the same. This was in June and July in this atmospheric river in the Antarctic Chilean station, and you can see here snow. A few days later, icy, no snow, dirty from the mountain because this wind usually takes dust from the mountains near the place. If you are during summer with the sun, this dust from the mountains goes to the glacier and it receives more energy, so the negative mass balance is higher. So it's like a circle. So this is what happened with the Earth connected with the air, above the surface. So we have seen several things: connections below, over, water, and so the challenge is put everything together. There are international initiatives, multidisciplinary, because we are talking about here different science into the earth sciences, but there are physics sciences, biological sciences, life sciences. There are some. Yesterday I saw a poster. When the ice retreats, then you have some vegetables, for say something. I say grass in Antarctica, but it's like grass, but it's the Chansia or lichens. They appear not from one day to the other, but after you have the retreat of the glacier, in several years, they appear. So they are linkage, and that's the reason we have several challenges to put everything together, work together, and use the effort, mainly the efforts, logistic effort mainly, are huge, very expensive, so we need to try to use one effort to cover the most possible of the science that we have. This is a map you can find in the COMNAP Antarctic facilities. This is the address. This is information from all national programs. You can see in red that's the most, but they are temporary stations, and in yellow, the permanent station. You can see here that the continent is huge. The amount of places where people is living during the whole year are few. So if we need to do something, or we want to do some research in some place or something in some area related to a region, for sure we need to contact the nearest station, people, crew, country, and do common efforts. Because if all of us goes of ourselves, the result for the scientific community will be less than if we are going together. For example, yesterday we had a talk about the Rings Action Group, and you can see a diagram for a paper in review from Matsuoka, and showing what is left to do and distance to science data all around Antarctica. The action group aims to go rings on the coast, and you can see the proportion. Only few areas of Antarctica is covered, and even though it's less, it's a few information that we need to make joint collaborations to get covered at least this part of Antarctica, only the coast. We are we are far from this. Related with this, other project related with rings was from the Sweden Rings campaign last year. They did a circumnavigation all around Antarctica with 2 twin otters and helicopters, with a huge effort with these instruments installed on the aircraft, and was a international collaboration. First was a private expedition. There was some money from a private funder. It was good because it was a huge operation, about more than 1 month, just flying all around Antarctica, and that is mean you for sure you will find bad weather somewhere. You cannot expect that you are going to be in Antarctica 2 months with 2 sunny days, so 2 months of sunny days. So something will happen, and so this risk is of course taken. But with the collaboration of this station, we have seen in the common map facilities, they reached it and could done all the round circumnavigation, and there was also support for the ship that was coordinated by Jefferson, going around Antarctica at the same time of the planes, taking fuel and some support, and they also take the opportunity to do some multidisciplinary research from the ship at the same longitude as the twin otters were flying. So they were primarily the support of the mission in the continent, and secondary, they were doing some other research in the ocean, in the earth, in the air. So this is kind of something that is very nice to do and participate. So we can, in this case, connect the earth sciences with the life sciences, with the physics sciences, logistics, all together in some project. It's not so easy. I don't say we are going to do this every year, but it's something that is important from the point of view of the earth sciences and the connections with other sciences that we are just the base, the stratus of the Antarctica, and everything happens in Antarctica, so everything's connected. Other thing that is important also, not easy also again, is the mass balance of the glaciers. This is a map of the glaciers that has been monitoring for several years all around the world. In Antarctica, we have only few in the northern part of the Antarctic Peninsula. Again, this is a glaciological method. You have to go to the glacier, walk the glacier, make a camp. Not so easy again, but for sure, we are underrepresented in this kind of collaboration information. So mass balance are estimated from satellite images, gravimeters, GRACE data, lasers, rings. Also, action group aims in the future to collaborate to get the mass balance everywhere. Maybe it's too difficult to go glacier by glacier, so one of the things is, okay, we go for the whole Antarctica. So we put a very huge satellite and we take a picture of the whole Antarctica and we get something about the whole Antarctica. The whole Antarctica is losing tons and tons of ice, so it's enough for the first approach. But then when you want to compare with different places in the world, it's not so easy, because if you want to take one small glacier, not so small, but some glacier in Antarctic Peninsula, or not the big ice shelf, for example, or the ice streams that are huge, it's just a spot, one pixel in the satellite images, so it's not so easy to take information from there. Another international collaboration, I guess everybody knows, but is the International Plenaría. You can find that it will happen sometime in the future, not so far, not tomorrow, but this is something that we also have to take care of, participate, and look for partners, look for fundings also, and look for other colleagues that are working in the same as we are doing and try to collaborate. Other thing also is Antarctic Inc. that is also working at the moment in meetings for put all together activities, synchronous activities. We also were discussing here that, and most of the things I was presenting is about the present, ongoing dynamics, ongoing features, how it's changing the weather, how it's changing the Antarctic system, but also we were talking on Monday about including paleo activities in these systems, in this collaboration, because, as I say before, the past is useful for knowing what we're at the moment and what will happen in the future. So it's something that also we have to take care to connecting everything. Here in the website you can see, connecting ice, ocean, climate, life protect, everything connected. So this is also part, Antarctica, earth science of the Antarctica, it's part of Antarctica, so should be there. And you can go to, for example, something that also arrested here, you can go to the SCARS website, just click here in science, and we'll see all these disciplinary groups, action groups, expert groups. There are several groups in the SCARS system, and something that's I don't want to say usually, but often, that you have a problem with the communication, and sometimes we want to do something, and we are in the group in one point of this website, and we are trying to find some information, data, and fighting with the, I don't know, with the Google, and fighting with the publishing papers, and it suddenly maybe something in the other part of the website is working on that and have the information. So it's just a matter of, instead of fighting with the computer and internet, just contact someone in the system. This is a collaborative system, so you can contact someone everywhere here, everyone there, and say, okay, do you have information about the glaciers do you have information about the tectonics in that part? So it's something that I encourage everybody to do, because here we have the connections. Of course, earth science we have here, the first one, of course, earth science first. And then you have different things, life, or co-physicals, cross-disciplinary here, and this also is important because they exchange information with other countries, in other forums. So something that we have to do is check others, what they are doing. And for example, this symposium, we have seen several things, opportunities of or devices of taking pictures and models on the place, and that maybe one uses, okay, I use this for modeling or printing something about the rocks. But maybe someone say, I can use it also for glacier. It's good enough. So this is a place to connect everywhere with everyone. And the last things, new tools. What is new tools? Last week, we had the release of ChatGPT 5, new version, and they are going fast because version 4 was a few years ago, and version 3 latest, they are improving very fast. Okay, you cannot ask ChatGPT how to give me the projection of my glacier in 5 years, but something you can do is, for example, ask, give me a code in Python to plot the graph with the machine learning. I just tried this for this presentation. I just put in the chat. I need a plot for a PowerPoint presentation, only one graph with the machine learning diagram. It gave me the code in just about 10 seconds. I ran it in the Python, and I got this in a file and just placed here. So this is something that is very useful, and a lot of people, young people most, are using with, for example, the cookies. And just you can find Google. I need a code in Python to process satellite images to get the snow index, vegetation index, I don't know. And they found it very fast, and they execute it very fast also, and we found good results. So it's important to have in mind the new tools. With this in mind, there was a collaboration here, regional, in South America, with people from France also, about a workshop of glaciology, working mainly with this kind of tools. One of them that we are working at the moment is the mass balance machine model that is use machine learning. You can see linear regression, neural network. Everything is something from the artificial intelligence, different branches, and then they have the opportunity, they give you the opportunity to put several information. We have information about this. Please try to learn something that maybe in the past we used to put in the, I don't know, transparent paper on the window and just to match two different graphs. Okay, now it's done in 5 seconds by the computer. So we need to use it. And other project, for example, is CryoTools. That is, you can see here, it's called CosiPy. But what does it mean, CosiPy? It's a change from Cosima, that is MATLAB, change it to Python. Because MATLAB is more difficult, and Python is used by everyone. And you can find in ChatGPT, I need a code in Python too, and it's appear magically. So we need to know about this. We need to use this. And in case of glacier again, in the glaciology, so sorry, but in the case of glacier, as the same we were talking before about the simulations, numerical simulations of the Antarctica. In this case, we have an open, usually all of these are open source code, so very important. Open global glacier model, that the CosiPy projects and the mass balance project you have, they give you the notebook receipt. You just put run, and you have information and data, almost always. But sometimes, for example, in my case, I have tried something in Antarctica. The modeling is not working pretty well. The information about DMs, digital elevation, conditions, for example, ERA5, the new release ERA5 data set that is used with one of these models has not been calibrated and tuned for Antarctica. So when I try to put the coordinate for Antarctic Peninsula, they say no data, no data, no data. So it's a very nice tool, but you need to take care of two things. First, check that it's working in your region. And second, be sure of that, because if you sometimes you got numbers and you say, okay, it's working, but they are wrong numbers. They are just fictitious because the sim is not pretty well, but this is something we had to use. It's a tool, and we need to use it because it saves a lot of time to reach what we were working and finishing. And the last, I guess, is one of the last one, other machine learning model for use it for the seismic activity processing. Then you can find here deep learning for automatic identification of the signals, waves, and timestamp to check, to find something that maybe is hiding to your eyes. This kind of flow chart and models find you for you very fast. And I guess, last one. Use the new tools. Learn about the new tools because you can download or ask for ChatGPT, but you have to know the background about this. I'm ready.
Thank you, Sebastian, for your overview. Very, very good, actually. An update with all these last tools that you showed. That, yeah, it's amazing, actually. So we have time for 2 questions. Please, don't be ashamed.
Coffee time.
Or comment that you want to make.
I'm dying to hear your response to the following question. So you remember the slide that was the SCAR website and it had the breakdown of all the different organizations? I've always been curious as to why there's no specific designation for law and international relations. Now, I do realize there's a policy button, and then it takes you to the Antarctic Treaty and the consultative parties and stuff. But there's no international law, international relations, specific concentration from an overall perspective. So I'm curious, help me see.
It's not my subject. Here we have people from SCAR directly, we can ask them, but I can say that the Antarctic continent has not the government, so it's a treaty system. So everybody goes to the meetings, do proposals, everybody agree or disagree, and we are just in a matter of a common agreement. So maybe this is the reason. I am just a glaciologist, not lawyer, but we can ask later to the people. I cannot, maybe we can also ask if we need to add something for artificial intelligence there. But
Yes, that is true. Actually, I think that SCAR started actually as a physical air science mainly, but lately, probably 10 or 15 years ago, SCAR started to incorporate also social science. And I think in the future, and also there are people from the law working in Antarctic issues. So I think in the future, probably you are going to see something what you ask. Okay, so let's take a break for coffee and relax.